Okay, let's get things started. Good afternoon, everyone, and welcome to CISA 24's final keynote session, Enabling Discoveries of the Hidden Universe. I'm Jim Myers, professor in the Space Studies and Earth Sciences Department at American Public University System. I will be the moderator for this session. And it's my honor to introduce Carl Starr, our speaker. He has a long history working in space operations and engineering in the military, government agencies, and in the private sector as well. Most notably, he was the leader of the missions operation team that shepherded the James Webb Space Telescope through its launch and commissioning. Carl's also a graduate of APUS's Space Studies program with both a bachelor's and a master's degree in space studies. We will be taking questions in the chat, and we will have a session, a Q&A session after Carl finishes speaking. So if any questions come up during the talk, please feel free to enter them in the chat. And without further ado, Carl, I'll turn things over to you.
All right, great. Thanks, James. Appreciate it. Sorry, everybody. It was me that caused it to be a little late. I had the wrong link. I'm so sorry. So I'm sure everybody's heard that before. Let me just double check. Jim, how long do I have? What's my cutoff time?
The session is scheduled for until 4:40.
Perfect. All right, perfect. That's plenty of time. So what I'm going to do is I have several different sections that I'm going to go through. Each of them has kind of a natural break. And so if questions are kind of being asked in that particular section, before I go on, I'll just go ahead and ask you, Jim, to go ahead and read if there's any questions or if anybody has any questions at that time before we go to the next one. So there's about 3 different sections. So we'll go ahead and do that. And then along the way, I have some videos that I want to show, and then I've got some special things for those that decided to dial in today that you won't see anywhere else. So a little teaser there. So all right. So with that, let me go ahead and get started. So my name's Carl Starr, as Jim said. I come from Chicago, and my family moved to New Mexico when I was little, around 10 years old. And it's kind of an important time frame for me. That was when I first started to realize that I wanted to get into space. And specifically, there was one incident in New Mexico when I was little. I remember it. I don't know why I remember this one, but I was young. It was in the summer, and I remember laying out in a field of alfalfa. It was late at night, and I was just laying on my back looking at the sky. And I was tracking satellites as they were crossing the sky there. And my mom came out. She was looking all over for me, and I hadn't responded. And here I was laying down, in this field. Anyway, she found me. She said, "What are you doing?" And I said, I'm looking at, you see those things up there? And I tried to get her to, watch as they were tracing across the sky. I said, "Those are satellites." And she said, "Oh, yeah." Right then and there, I told her, I said, I want to fly one of those. That's what I want to do. And she was just like, "Okay, you could do anything you want, right?" But I kind of took that as, yeah, I could do anything I want. So that's being, night sky, big sky out there in New Mexico really kind of spurned me on my way. One thing led to another. I found myself working for NASA. Most recently with the James Webb Space Telescope. I spent around 20 years working on that program. I was the mission operations manager. I put that team together, put the operations concepts, put them into motion, helped get the team trained, and then kind of did it. Along the way, NASA was nice enough to give me a medal for that. I'm married. I've got a daughter and a little dog, little golden doodle. And she's 12 and just adorable. So, I mean, not the dog, my daughter. I'm also a bread maker. I do that on my part-time. I got a book there, and I am a mentor for APUS. And then most recently, I'm a part-time professor. So I teach the space studies program, different topics, and I've been doing that now for just over a year. Really like that. So that brings a big smile to my face every time a class starts. How did I get here to where I'm at now, to where I'm talking to you about? Well, first and foremost, I'm a Dale Carnegie graduate. So I I feel that you have to have mentors. You have to have someone give you, a focus or a reason for doing certain things. And I gravitated towards Dale Carnegie. I kind of took that, went to the military, spent 12 years in the Army, what was Army Space Command, what would be Space Force now. Had a real great time, but I started to excel at leadership. I was, obviously I talk a lot, and um, I learned how to speak probably a lot better from my time in the military and dealing with senior leadership and some of the types of jobs that I had. I then went on to work for NASA. I worked on the Chandra X-ray telescope, the EOS missions. I probably should have included the JWST logo in here as well, but we'll get to that later. And then obviously APUS, AMU, I am a graduate, as Jim said. So what I want to talk to you today about are 3 areas of space. And, my whole talk is enabling the discoveries of the cosmos. So enabling. So I kind of thought, well, how do you do that? How does one enable another person to discover things or find things out, or even be in that industry? And so when I put this presentation together, that was really where I was coming from, is how do you do that? How do you enable somebody? What would they need to do? So 3 areas I want to talk about: the commercial aspect of space. I want to talk about the military aspect of space, and then also science. There's probably other areas, but these are the 3 I want to focus on, because these are 3 I think resonate with what the school is doing, and I think what the industry is doing now. I've spent 30 plus years in this industry, and I do a lot of hiring, firing, jobs, programs, you name it. And I've grouped them into these categories. And so what I'm going to do is I'm going to show you a series of videos, and then I have something after. These are very short, so don't panic. I know you didn't sign up for like a movie or something, but I've got 3 very short videos that I want to talk to you about. And I want you, as you're watching them, try to put yourself into the position of, okay, maybe I'm in the industry, maybe I'm not in the industry, but where is the industry going? Where is the commercial industry going? Where is the military industry going? Where's science going now? And then more importantly, how can I participate? That's really kind of what I wanted to talk to you today about, is if you're going to enable somebody to discover things that are out there, these are 3 areas I think we can start from. All right. So that's where we're going to go. And then after we get through this section, we'll take some questions. So if you have questions already, hang on to that. Once I finish this part, we'll take a little Q&A and we'll move on.
Hello and welcome to this video. Today we are going to delve into the fascinating world of space exploration in the rapidly growing commercial space industry. From ancient times, mankind has been mesmerized by the stars and the mysteries that lie beyond our planet. However, it was not until the 20th century that we began to actively explore space. The launch of Sputnik, the first artificial satellite, by the Soviet Union in 1957 ignited the space race between the Soviet Union and the United States. This launch marked a new era for humanity, as we started to explore and understand more about our universe and the possibilities of space exploration. Fast forward to today, the space industry has grown and evolved to include private companies such as SpaceX, Blue Origin, and Virgin Galactic. These companies are not only competing with government agencies like NASA and the Russian Space Agency, but they are also driving the industry forward with innovative technologies and ideas. These companies are pushing the boundaries of what was once thought impossible and making space exploration more accessible and affordable for everyone. One of the most significant areas of growth in the commercial space industry is satellite launches. Companies like SpaceX and Blue Origin are developing reusable rockets, which can significantly reduce the cost of placing a satellite into orbit. This is making it possible for more companies, including small startups, to launch their own satellites and provide services such as satellite internet and Earth imaging. With the increasing demand for satellite-based services such as GPS, weather forecasting, and telecommunications, the commercial space industry is expected to see continued growth in this area. Another exciting development in the commercial space industry is space tourism. Companies like Virgin Galactic are working to make it possible for people to take trips to space, providing a new form of adventure travel and opening up new business opportunities. This new form of tourism is expected to create jobs, boost the economy, and change the way we think of space exploration. But the commercial space industry isn't just about launching rockets and taking people to space. It also includes mining celestial bodies for valuable resources such as water, helium-3, and rare metals. Companies like Planetary Resources and Deep Space Industries are leading the way in developing the technology to mine asteroids and other celestial bodies. This new form of mining could greatly benefit humanity by providing us with new resources and helping us to become more self-sufficient. It's important to remember that space exploration comes with its own set of challenges. The debris created by launches and space activities can be a hazard to satellites and spacecraft. And as more and more companies and countries begin to explore and exploit space, there is a growing risk of conflict and competition for resources. These challenges make it vital for us to have international agreements and regulations to govern the use of space resources and to ensure the long-term sustainability of space exploration. Despite these challenges, the commercial space industry holds enormous potential for the future of humanity. It has the potential to revolutionize the way we live and work, and open up new frontiers for exploration and discovery. With the advancements in technology and the growing interest from the private sector, space exploration is becoming more accessible and affordable for everyone. The commercial space industry is creating new opportunities for investment, research, and development, and is changing the way we think about our place in the universe. Thank you for watching this video. Please make sure to like, share, and subscribe to our channel Tech Trends for more updates on technology. Hello and welcome.
All right, so a lot of information there. I just put, as I was watching the video, obviously not now, but as I was putting this together, all of these topics were covered in there. Satellite manufacturing, rockets, ground support equipment. That's a huge topic just in of itself, just the ground aspect of supporting something in space. Everything that goes up into space has a ground or an earth counterpart because they don't just go up there by themselves. Imagery, tourism, IT, cybersecurity, communications, all of these things were present there. So just in one aspect of those three main categories that I wanted to speak about today, all of these things are present and prevalent. And again, when you're enabling somebody to make discoveries, or when you're enabling somebody to do something in space, as you can kind of see here, some of these things are not actually in space. You don't have to be the person that goes on the rocket, right? I'll never go on a mission to space, but I'll be more than happy to help you get there, right? I have no problem helping somebody make the parts or putting the infrastructure together or the IT together, all of those things that make it possible for a person to do that. But I certainly don't want to be the one that has to go up there. I know what it takes to get to space, and there's there's no way I could be an astronaut, no way. But nonetheless, these items here, it's not just about rockets. It's not just about building satellites. It's not just about building telescopes, right? There is infrastructure also that the commercial industry is participating in now, and it's starting to branch into many, many different things. For example, one thing I didn't put on the slide, but there's a whole Better Business Bureau now for space. One of my buddies, he's an APUS AMU graduate, and he is working for the Space Better Business Bureau. They've got a name, I forgot what it was, I apologize. But there's even that going on because space is booming. There's all kinds of different aspects, especially in the commercial sector. So that's just something to keep in mind, kind of put in the back of your head, because we're gonna bring this back. All right, one more. That was the longest video, by the way. These are shorter.
The U.S. has the most dominant military in the world, but recently experts have been warning that it has a weakness: its reliance on satellites. Satellites are involved in nearly every military operation: communication, intelligence, radar, drone piloting, and even coordinating troop movements with GPS. But Russia and China have been developing the means to attack satellites. Aside from simply shooting them down with missiles, those countries can also use lasers or electronic jammers to block satellites' ability to communicate. Hackers can also try to attack satellite software. And satellites are inherently hard to protect. One national security professor told Politico that a satellite is basically a sitting duck. It's easy to track and can't be hidden. There are some efforts to make the satellite fleet harder to destroy, like launching lots of backups. But ultimately, the military is relying on deterrence to keep its satellites safe. That said, if the US were to get into an open conflict with Russia or China, analysts fully expect satellite attacks to be one of the opening moves. It's the easiest way for either country to try to shrink America's military advantage. With that in mind, the military has already begun training troops on how to function if key space-based systems get knocked offline.
Let's take a look at some of the things that were brought up here. Ground-based and space-based systems to monitor ballistic launches. That's one very simple bullet, but it's an entire industry. There's corporations out there that for the last 40 years have done nothing but just implement that first bullet. And it's going on today. The US military, the Space Force, SDA are changing the way that it approaches how to deal with that first bullet, how they're monitoring ballistic missile launches and what to do about them and how to get that data, more importantly, back to the ground. The space surveillance sensors. People should realize that there's a symbiotic relationship between the military itself and, believe it or not, NASA. NASA is very science, not military. However, a lot of sensors, a lot of technology developed by the military, paid for by the military, and then NASA takes advantage of that. Obviously not to blow people up, but they take advantage of using a different sensor or using something that is surplus that they can put on a different vehicle and use it for science. So people should just be aware of that. Communications, obviously most everybody knows that you can pick up your phone and call. Signals are going around the ground. They're hopping through satellite terminals. Now, if I'm not mistaken, they've got technology now with your cell phone. You can make a satellite phone call anywhere in the world. You're getting internet everywhere. The military is doing that as well in their own realm. Navigation, obviously GPS, and then transport. What I meant by that is really rockets and sponsoring rocket launches. There's this thing called rideshare now where, basically the rockets are big enough now, the satellites are smaller where there's a lot of room for everybody. So the military will purchase a rocket and kind of rent out, if you will, the lower half of it or a section where somebody else can launch their rocket, their satellite into space. So again, this is another kind of the second biggest area of space besides commercial applications. You have military space applications. One more to go.
Carl, I don't think the audio is coming through properly on that. At least, I'm not hearing anything.
When does curiosity become a fire? No more to unlock the doors of discovery and open up fascinating new worlds to explore. The bird can fly for long periods of time, but why can't I? Man, you go, Martin. Chandra, Is entering the last leg of its journey beyond the edge of our soul. The universe so vast and so distant. Never been busier in space than we are today, using the new frontier, all its wonders, to solve the challenges of life here. To set a course, to go farther, and achieve more than we have ever done before. The future holds untold opportunities. We will expand our presence beyond the International Space Station. Today, the Earth's sole permanent off-world outpost. Tomorrow, just one critical element of a bustling hive of work and wonder. We will continue to partner with leading companies across the nation and with other countries around the world to ensure safe, regular access to Earth orbit and beyond. Developing new vehicles that can travel away from our home world. Vehicles that will propel automated probes and robotic and human explorers to other worlds and other destinations. Gaining new knowledge on resources, expanding our reach across the solar system. We further space-based studies of our own planet to protect our resources and enrich human lives on everyday life. Just as exploration of space has always done. In its 50-year history, NASA Research and Development has delivered more than 2,000 breakthrough technologies, new medical tools to aid laser surgery, replace lost limbs, and create brighter smiles. Safety products to assist and protect fire and rescue workers, improve air transportation system that make air travel safer nationwide, and consumer products such as mobile headsets and freeze-dried foods. Thousands of innovations, big and small, all folded into our daily lives, making them better, making us safer, making the future take flight. Where will tomorrow's technologies take us? In the hands of new generations of scientists and engineers.
Some experiments to be conducted by the first people to land on Mars. I will help discover the first Earth-like planet in a known star system. And
The future begins now. It begins with you.
All right. Science space applications. There's basically some very basic, there's some key points here about science. You can divide all of science space applications into solar and space physics, exploration of planets, moons, asteroids, comets, anything in the solar system. You can study the origin of evolution, current state of varied objects. You can research non-living materials or living materials. And then also you can study space. Instead of looking outward, you can look inward. So altogether, between commercial applications, military applications, and science applications, there's a lot there. All three of these things, I feel, can enable someone to get to space. And that's really, again, the crux of my point that I'm trying to make today is, well, now that we know what there is out there, you know, how do we do it? What can we do to actually get there and make that happen? So, Jim, I'll ask you right now, there's a kind of a natural break before I kind of digress into the next section. If there's any questions that you want to bring up, now's a good time. I can answer them just on this section here.
Sure. The only thing that's currently in the chat is someone asking for the video links.
Yes, the video links are at the end of my presentation, and I will load the presentation later. You can have everything, so totally fine. Yep. Totally.
Okay. Let's see. I don't see anything else popping up right now.
Fine. All right. So let's move on. What does it take? How do we get there? We know that there's commercial, there's military, there's science. What does it take? These are the three areas that I focused on, and these were all of the topics that we expanded on. And so really, how do you get there? How do we help people participate in this industry? And again, more importantly, on the bottom right, what foundation do we need to succeed in any of these, in the commercial area, the military area, or the science area? What exactly do we need to be able to make this happen? Because again, a lot of people, they look up into space, they see things around them, they watch TV, and they just don't know how to get there. They just don't know, and they want to. So that's what I want to try to do, is to help people actually bridge that gap and give you a vehicle or a tool to get there. So what I really feel like is that the school is very well positioned and structured to get people into space. So if you look at these three areas, and then you start looking at what kind of degrees, what kind of topics are there that enable these three areas, everything from space studies, computer science, IT courses. These are all space applicable degrees. And what's even interesting is these are all degree programs that APUS offers. And they directly relate to the three videos that I just showed you. They directly relate to those three topics where I expanded them and gave you thoughts to talk about in each one. The school does all that. And so you kind of see where I'm going here. If you want to kind of get to space, APUS is a way to do that. And I say that because, we hire graduates, we move graduates around. People are asking all the time, how can I do that? We have a very good network already established and getting better to help people into some of these positions. It's important also to know that even though that you get that kind of training, you get that degree, you've got to be careful of the fact that the workforce has been changing and the workforce is under constant change. For example, remote access. More people are working from home because they can. COVID kind of opened that right up. And for those that don't know, but the Webb telescope launched right in the middle of the pandemic. And on any one day, I think I had 200 people locally on shift 24/7 day and night at the Institute doing mission operations and commissioning JWST. But I also had 2.5 times that amount online that we're supporting. So I had more people offline supporting launch and operations and commissioning at home than I did in the building. And we had to end up practicing like that. I think other companies kind of did the same thing. They found themselves in this position and figured out how to make it work. Now that we did that and we're all here to talk about it, here's the paradigm, right? People can work from home. Not every job, but a lot of people in IT can. People in my business, in the satellite building business, there's certain jobs that you can do it. Unless you're making a component in a clean room, chances are you can work from home or in a hybrid situation. So people should be aware of that. It's out there. Because that there is remote workers out there, one thing to be aware of, just like with school and just like with how APUS kind of addresses this, is you can become detached. Maybe your job is hybrid, maybe it is 100% remote, but as you go into the industry, as people, as our students go into the industry or our peers, we should all be aware of the fact that you could get really lost in the fact that you're just there by yourself. So you have to be able to adapt, whether that's in a hybrid environment. You have to understand that there's people that work in different time zones, just like how the school accommodates students that are around the world at any one time going to the same class. One of my classes now, there's students that are in Japan, and there's students that are all across the country. I've got all kinds of different time zones to keep up with, and yet somehow we make it work. The reason why it works is because there's a very big emphasis on communication. I think that's a key takeaway. Knowing that you want to get to space, knowing that APUS has courses for you and degree programs for you, you've got to be able to communicate. It's imperative. If you can't state your case on one slide, what the problem is, what the impacts of that problem is if you don't fix it, and then a potential solution. If you can't do that on one slide, it's going to be very difficult for you. So what's going on now, at least in the space studies area, is there's a lot of emphasis on better communication, even putting presentations together that get your point across so you can communicate, because it doesn't matter what degree you get. As soon as you go out into the workforce, people are expecting you to communicate, and those that can elevate quickly. And what I truly believe is that APUS addresses all four of these things very well. Obviously, it's remote. There is because there's constant communication, people are included. So there's nobody kind of left behind. So you don't get that feeling of isolation. You have to adapt. And then there's definitely an emphasis of communication. So I see the school definitely moving the student body, and the industry in this way. They're already doing it. They've been doing it now that it's personified that way. How AMU specifically complements the workforce. I think in preparing students for leadership in a diverse, just a global society, again, because we're already dealing with people that are all over the place, we embrace remote learning and remote collaboration. Again, when the industry now, commercial science, even in some military applications, even some of the Space Force people we support, you'll call up and you'll be on a phone call, and that colonel is working from home that day, or this master sergeant's working from home. And it doesn't matter. It doesn't matter where you are. You can still collaborate. You still get the job done. I think that's really important. Again, effective communication, time management skills. That's something that everyone is taught. You're kind of forced to do it. I think the school does very well at it, because most everybody here is not everybody, but there's an awful lot of non-full-time students here. There are people that have jobs, people that are active duty, people that are retired, people in 2 jobs, and yet they're still figuring out and succeeding at how to get to school. And there's ways to do that, right? Even APUS has the first course you take is how to manage your time. Some tools that can help you. And then also the forums, very important here. Forums are a way to do all of these things. You can lead in a forum. You can collaborate in the forum. You certainly learn how to communicate in the forums. They're due at a specific time. So again, time management skills, all of these things factor in. So I think anybody watching this, whether you're going to this school or not, you should know that this school is doing it. And what can we focus on? The industry needs people with different backgrounds. And it doesn't always have to be space related. It's something else that can support the space industry. For example, somebody that's good with just computers or databases, that's fantastic, because, once you know it, most everything that goes into space runs on a database. You may not be building an avionics component. You may not be the astronomer that's going to use that component, but you're the person putting the engine together on the ground of everything that's going to use that data. That's very important. So you don't really have to be, somebody that is designing a propulsion system or designing the latest Ka-band antenna or anything like that. You could be an IT person. You can be somebody that just runs those software programs, somebody that's a system administrator, somebody that's involved in cybersecurity. That's really big. All different aspects can support the space programs. I showed you on those previous slides. When you start talking about commercial, military, and science areas, there's a whole lot of things that go into just putting something into space, and more importantly, keeping it in space. Most every vehicle is flown from the ground. It may not involve real heavy time interaction, but there's always somebody on the ground that is doing something. Case in point, when the Spitzer telescope was up there running, I bring that up because I have something about that later. But anyways, we were putting together a plan of how we would operate JWST. And at the time, this was in the early 2000s. So gosh, we're dating myself. So it's already going on 20 some years. We were doing a Q&A at some NASA sites. We happened to go to JPL. we were asking them, hey, how do you work with your communications and how do you operate your satellites that are up there? And at the time, they had the Spitzer telescope. So, all right, great. So we walked into the control room and it was kind of small. And there was 1, 2, 3, maybe 4, 5, 6 places to sit. The whole room was empty. The lights were off. And we were all old school. We were people come from the military and different backgrounds. And we're like, well, where the heck is everybody? And our tour guy he said, just stand over here. He looks at his watch. He's like, all right, just wait. We're looking at the clock. Yep, on the hour. Hold on. So we're standing there in the dark. 2 guys come walking in, flip the lights on. All of a sudden, the computer terminals turn on. The screens get active. There's telemetry coming in. All kinds of things are going on. We're just watching. And these guys are going over to this terminal, looking. Then they go over to this terminal. They're looking, going over here. Did what they had to do, and they were gone in less than 10 minutes. And that was it. And we're like, what the heck just happened? They were just monitoring automatic transfers of data that were coming down from space, making sure that that data got routed to the right places, making sure that the vehicle was safe. There was all kinds of things that were going on, but it was done in a different sense than what we thought. So I'm just trying to illustrate it may not be what you think space is, but everybody has some of the basic tenets that go into putting something up there, keeping something up there. And that's where the commands and telemetry come in, and also learning about that software and the databases. Automation is key, like I just illustrated. And then really what helps is, if you know something about space, that's fantastic, because that goes a long way, believe it or not. And I know some people think, well, what do you even mean by understanding space? There's a course in the space studies program, and it's a history course basically about space and how the space industry started and where it is today, and talks about, Sputnik all the way up through today. And what's really interesting about that is there's different forums and different questions to lead you through it. But you start to learn that, number one, it's not very old. So it's kind of easy, when you compare it to world history, that's kind of old and there's an awful lot to digest. And then even American history, that's still a couple of hundred years plus. Space history, it's not that much, right? There's not a whole lot that you have to go back to. So I feel it's something you can kind of wrap your hands around. Maybe I'm just lazy, but you can wrap your hands around 40, 50-ish years easily. And you can understand who the key players are, and more importantly, who those players are now today, because it's the same players, they've just changed their name. And so it's very good to understand your roots, where you come from. Reason why I bring this up is, let's say you want to be in the space business, whether you're an astronomer, whether you're an engineer, or anywhere in between, and you want to go to work for NASA. Great. There's only 7 different NASA centers. You should understand the history of each NASA center. Again, it's not like world history. You don't have to go back for eons, but understanding what that center does. How is Goddard Space Flight Center different from JPL, different from Marshall Space Flight Center, different from Applied Physics Lab, et cetera, et cetera? How are these places different? What do they do? Why are they different? Why is Johnson Space Center different from Kennedy Space Center? These things can help you when you're in the workplace, just to even have the simple conversation, right? Like, what's going on. Maybe why it's like this. Why is the culture at this particular place the way it is? Same thing can be said for the military, how the military got its start into space, how it's propelling it now. If you've been paying attention for the last several years, the Space Force is pretty new. Prior to the Space Force, we had Army Space Command, and we had Air Force, who monitored most everything in space. Now it's the Space Force itself. So everyone, probably on the call is more than several years old. So you're participating in history as it's evolving, how this other tenet of the military is taking hold, what its missions are, what it's going to do, what it's going to address. These are very important if you're going to be in the space industry, is to understand these things. And then again, the other thing, again, I keep hammering out, you've got to be able to communicate. It's obvious when somebody graduates, at least to me, and we hire them, whether they're a master's or a bachelor's, depending on the school. Some schools don't teach communications, and that's a shame because it's obvious when you're immediately thrown into the workforce and expected to do something. So when you have these classes, if you're at APUS and you're doing some things, focus on those forums, focus on those group projects, focus on getting your point across in the smallest amount of words possible. How to be effective, how to be efficient. All right, so that is, I want to pause here. If there's any questions before I go on, I know what some of you are thinking. I'll come right to it. But are there any questions I need to address right now? Jim, are there any questions?
Nope, there are currently no questions in the chat.
All right, great. All right, so I know what some of you are thinking. Hey, come on, where's all the JWST stuff? Where is it? It's coming. All right, so what can you do? First, be a mentor, get involved, and be like TSA. If you see something, say something, okay? Really, that's all I wanted to say. These things really work. Pay attention to what you're doing. Volunteer to do things. Do a talk like this. Do an interview. Do something. The reason why I think it's important is because it forces you to go out into your industry and to find the latest and greatest so that you can share to your mentee, so that you can talk to people about what is the latest and greatest. If you're not participating, you just won't know because the latest and greatest is changing every day. All right. I got bonus material. I think this is probably the only reason why I ever get asked to come back and do these presentations. So I've got some things that nobody's seen before, obviously. And I'll get into that right now. So my bonus material is from one of my real good friends, Dr. Jane Rigby. I love her to death. She and I have worked together for a long, long time. And this year she was awarded the Presidential Medal of Freedom for all her work that she's done. She is a super cool lady, and she always has a way of breaking science down so that it's easy to understand. So I asked her, I told her I was doing this, and I said, you know, they always want me to say something from the project. Can you give me something? So she did, and I have that material. But just so you know, Dr. Rigby is not just my friend, but she's well renowned in astrophysics. If you just look, I put up here all of this information about Dr. Rigby. I was going to put more information about Jane and who she is and where she's from, but her bio is 26 pages long. I'm not kidding, 26 pages. So I kind of had to sum it up just in the fact that, you know, here's the number of papers she's written or been referenced. If you look her up, you'll find her. She's very easy to find, and she's just awesome. So we had a real good time working on the program together. She still works on the program as the senior project scientist. I no longer work on the program, but she does. And so she helped me out with these slides coming up. So all of this next material is from Dr. Rigby. All right, so let me get my notes out and I can talk to you all here. So this was the deep field that we took on JWST. And for those that don't know, and if you ever take my classes, I do explain this when it comes up, but what had happened here was we were still commissioning, and we were trying to understand how powerful the telescope was. And so the telescope manager, Lee, came in one day and said, hey, Carl, we're doing all this stuff, but we need to stare at something for a while. And I said, what do you mean for a while? And he's like, well, I need a few hours on the telescope. And so at the time, being the mission operations manager, I was in charge of all the time on the vehicle. I had to make sure that we were doing what we were supposed to be doing and nobody was just playing around. Not that Lee was playing around, but we wanted to play around. So we wanted to see how strong was JWST. So we looked at this for just a matter of hours. And, this is what we saw. And people see that now, and they see the images that came out of the first images of the deep field. But what you're seeing here is images, if you're going back, more than 4.2 billion years ago. These are some of the things you see. And then the distorted galaxies, the ones that are all bent, those are magnified by the gravity of different galaxy clusters. And these are from 8 to 11 billion years old, so around 9, with a redshift of 1.38. So if anybody understands, so I'm going to have a bunch of numbers up here coming on these charts with Z equals whatever. So it just to help you out, if it's Z like 0.1, that means it's 10% as the age of the universe for how the gravity was condensed. So if you're looking at this Z and it's 1.38, that means, well, it's very old, and you can gauge it by how old that is. 9 billion years equals that Z. And then if you look even further, when they analyzed a spectrum there from 13 billion years ago, that redshift was 8.6. And these are some of the galaxies that they were able to image and use the spectrometer, perform spectroscopy on those targets. And this is what they're seeing. This is the data that they're getting back. So they're taking some of the original data, now they're going back and they're reanalyzing it and finding out that these things are truly very, very old. So if you have a Z of 1, there's Z of 2, greater than 2. The higher you go, the older it is. So just think of it that way. So for those who don't know about redshift, when you're looking at light, and as the light ages and the universe expands, it goes from the visible to the infrared. And that's called redshift, right? And so the higher the number, the older it is. That's just, I guess, the only takeaway to make it easy for everybody. Higher the number, the older it is. You see there, looking back at some of these 13 billion years ago. I brought up Spitzer before. These are science images. This image on the left of your screen is from Spitzer. It is a real image. If you look at the same spot on the right, that's what we see with JWST. It's the exact same picture, just new and improved. Right? What strikes me about this, so, not to slight Spitzer, but if you stop to think about it for a minute, everybody up until, a few years ago was working off of images like the one on the left, doing good science, really good science with it, with that on the left. Look at what they got now on the right. I just find it amazing. Okay, here's a little animation. This also from the deep field that was taken. This was the real deep field, not just a test image. What's amazing about this, as we kind of zoom around, is this is a real image. And when the computer ingests it into the model, you can see what's going on here. It's kind of like 3 dimensions. Almost everything you're looking at is galaxies, by the way. The stars are really small inside the galaxies. Almost every single thing you're looking at is a galaxy. The redder galaxies that you see are older. If they're lighter in color, they're less old, okay? But if you find something that's very red, that's very old. Anyways, JWST was kind of poking around, and, they're looking through these images, and you can kind of see as you keep going back and back and back, going way back, they found this image, which is Maltese Galaxy. This has a redshift of 11.4. This was how it looked 400 billion years, 4 billion years after, 400 million years, sorry, after the Big Bang. So 13.4 billion years ago, 400 million years ago, after the Big Bang, that's what came out. And then we see it 13.5 billion years later. That's just amazing. So, and again, you see how there's 2 references here of the scientists that had this image and were analyzing it. They're taking images, they go back and they keep looking at those images and they find different things. But again, 400 million years after the Big Bang, this was there. And then it took us 13.5 billion years to go. I like this picture only because this is the Ophiuchi, the Rho Ophiuchi cloud. It's only because it's very difficult to say. Ophiuchi. This is named after the bright star in the region. And this is in the north plane of the Milky Way. and it's bordering on the constellations of Ophiuchus and Scorpius. This image came out a year after we finished commissioning. And this is the closest star forming region to Earth. And that's a real picture. All right, last one.
Cassiopeia A, or Cass A, is a supernova remnant located 11,000 light years away in the constellation Cassiopeia. Cass A measures about 13 light years, or 76 trillion miles across, and is estimated to have exploded about 340 years ago as seen from Earth. In this image of Cassiopeia A, we witness a complex and dynamic system, a star that has explosively shattered, creating a shock wave colliding with the gas shed by the star before its explosion. The white smoky light is the aftermath of this event, representing radiation produced as the forward shock wave encounters and interacts with the surrounding medium. While Cass A has been observed by many telescopes, Webb's high sensitivity reveals never-before-seen details. Within this image, we encounter minuscule fragments, tiny ejected bits of stellar debris comprised of sulfur, oxygen, argon, and neon, shown here in bright orange and light pink hues. The dark voids in the scene are caused by some of the minute fragments acting like shrapnel, piercing through the circumstellar gas and leaving a trail of cosmic bullet holes in their wake. Also present are what astronomers call light echoes. With these light echoes, we're seeing where the original light of the supernova has been absorbed and reprocessed as infrared light by surrounding interstellar material. It takes many years for the original light to travel this roundabout path. By observing this journey, astronomers are able to learn more about the object that emitted the light in the first place, the composition of the region, and the distances between celestial objects. Finally, we visit a particular light echo from an area filled with intricate dust patterns. Nicknamed Baby Cass A because of its proximity and connection to the large supernova, Baby Cass A appears to be nearby, but is actually located 170 light years behind the supernova remnant. The unprecedented detail captured in this new image of Cassiopeia A has allowed scientists to discern intricate small-scale structures within the remnants of a supernova. This newfound infrared clarity, only possible with Webb's instruments, enhances our understanding of the processes surrounding supernovae. By studying objects like Cass A, astronomers can unravel the complexities of stellar explosions, trace the distribution of elements, and gain valuable insights into how new stars and planetary systems form.
All right, that's I leave you with that. That's enough. So, all right, Jim, any questions? More than happy to answer.
Yes, we do have a few. Well, of course, people are commenting how incredible the images are. And thank you so much for sharing those with us. There's a question about the red galaxy that you zoomed in on. They're asking if that's the oldest object that we have observed, and if not, what is?
That is the oldest object that's been observed.
Okay. We also have a question about really more about your earlier material. How did you get a chance to work for NASA, and do you have any advice for what steps we could take to work for them?
How did I get a chance to work at NASA? Well, let's see. I guess to be perfectly honest with you, with everybody, I really don't know. I was in the military. I was getting out of the military. I spent 12 years in the service, and I was already on my way. I was out processing, and some guys named Ron Felice calls me up and says, "Hey, I got your resume in front of me. You know, I want to talk to you about working on the Chandra X-ray Observatory for NASA." And I said, "Great, you know, Ron, I don't know you. I didn't send you my resume." And he never, to this day, never told me how he got my resume. I don't know. I already had a job. I had a job with another company, And but he said, wait, I will come to you. So I was in Colorado Springs at the time. He flew out, talked to me, showed me this chart, said, I think this would be a good spot for you, whatever. And come to Cambridge, Massachusetts. I want to show you what we're building there. So he flew me out there like the next week. I go out there and they had a position for me. And so I sat down at this desk and I called the people I was already employed with and I said, I'm sorry, I have to, I can't take the job. I'm gonna be here in Massachusetts. I know that doesn't help. So how can anybody go to work for NASA? So number one, the easiest way to work for NASA is to get into the intern program. If you can intern on any NASA center and do well at your internship, you will more than likely be hired. That's just the way it kind of works at NASA. The other way you can do it is, obviously you have to go to USA Jobs and fill it out and you wait. That is a really tough route to go. NASA, as large as that organization is, really does the cold calls. I've never seen it be that successful, to be honest with everyone on the call. I think you have to know somebody. You've got to know a project is starting. In other words, that there's work. Another way to get your foot in the door is when there is a project that is a NASA project. What you do is you go to work for one of the contractors first that is supporting that contract. There are here at Goddard Space Flight Center, I'm in Maryland, here at Goddard Space Flight Center, there is just a zillion contractors that support various programs at NASA. So what you do is you apply to one of those, you get into a job, and then you can transfer, you get to know the NASA people, and then you transfer in because they'll sponsor you. I think that's probably the easiest way to do it. You can try submitting a resume coldly, from USA Jobs, but that's incredibly difficult. And I don't think people have very good luck with that. But I think if you can intern or you can work for a subcontractor and then transfer over, like get your foot in the door and then they see how good you are, you just talk to people there and tell them that you want to be a civil servant and they'll definitely make that happen for you if you're good, for sure.
Okay, we have a few more. Is the Space Studies program a good avenue to become a science communicator?
I think the Space Studies program is good for anything in space. For a space communicator, if you mean media relations or something to that effect, you'd want to take some specific communication courses and stuff. But if you're just doing anything in space, space studies is becoming really more like space studies is becoming like an aerospace engineering degree. I know there's going to be other courses added to it to beef it up, but that's kind of the weight that it has, which is more on a technical side. There's a whole communication side that really, it's a good foundation, but then eventually you're going to have to take communication course if you want to be a facilitator like that, some kind of media, some kind of thing like that.
Okay, let's see. I'm going to do this slightly out of order just because the next question is also about communications. Now, this is from Professor Kristen Miller, but I know you're not a student anymore, so you don't have to be too nervous with that answer. She says, I completely agree that communication is the key, especially in online hybrid environments. At the same time, virtual communications have a hard time supporting the casual, collaborative communications that occur naturally in the workplace and that help develop scientific ideas and projects. How can we provide opportunities for these kinds of conversations in the virtual world?
That's a good question, Dr. Miller. I think really I agree with you. It is difficult. What I find that helps is, having, we're using Zoom and you can see me. I can't see any of you, but that kind of video interaction really helps. It's better than a phone call. It's better than a voice track. It's not the same thing as in person, but I think being able to do a video call goes a long way. The challenge is, especially at APUS, is people are in many different time zones, and that is very difficult to coordinate. It's not impossible, and the reason why I say that is because I'm here in Maryland on the East Coast. I manage a program on the West Coast. My customer is on the East Coast, but my entire staff is on the West Coast. So, and we do videos all the time. And that's one way we can, aside from visiting, that's one way that we do it is we definitely use the video conferencing. WebEx is what we use predominantly. We use Teams. We have other people in Colorado, and we do the same thing. If we find that if we can at least occasionally see your face, that goes a long way. It's not being in person, but it goes a long way. Because I could be yelling at you and everything else. You can't see me smiling unless you're looking at me. So you may take it the wrong way. Stuff like that really helps. And I think it helps build a rapport with a team when you can't be there in person. So I think there's things you can do. It's not a non-zero solution.
Okay. Final question that I see is, who do you think is the most important, I suppose, person in a rocket launch?
Who's the most important person in a rocket launch?
I guess they mean, what technical personnel is the most important person?
Yeah, I don't think there is one person. I've done a lot of launches. I've supported a lot of different launch campaigns. And even with JWST, everybody's job is so important. It doesn't matter. You could be the person who, like I said, you could be the IT person, and maybe somebody's going to give the final go, no go, but if their headset doesn't work or their computer breaks, they're ineffective. People have to understand the space business is really the ultimate team sport. It takes everybody to do it. Just even Dr. Rigby there is awesome as she is. She could not do her job as great as she does it without the 20,000 people it took to actually build it and get it up into space and continue to fly it, right? So it's a team sport. It really is. Everybody is super important. Everybody is. And I know some people act like their job is the most important thing or they're the most important piece to it, but that's not really how I see it. I don't think you're able to even the administrative assistants that aren't doing anything technical other than taking care of your logistics or your travel or your salary or your whatever issues you have. You can't do your job without that. So it takes a lot of people. I don't think there's any one person. I would not put one person above another. What I always say is, whatever you're doing, no matter what you're doing, you need to be the best at it. You need to do your very best at your job because it matters.
Okay, so checking our time, it looks like we have time for one more question that has popped up. How can we contribute to the space community for those with an interest, but not with relevant educational background?
Oh, there's all kinds of amateur space talks. There's all kind. Just Google, like amateur space talk in your area or something like that. There's all kinds of things that go on. I've got friends that have just telescopes, and they have look for telescope parties. The reason why I say that is because there's a whole like subculture out there of people that have telescopes, and they all go to these places, parks, national parks, whatever it is, and they advertise. I don't really know how they do it. I don't have Facebook or anything, but they advertise somehow, and they all just show up on a particular night. Everybody brings out their different telescopes, and ultimately people are talking and sharing and letting you look through the lens, and it's awesome. And if you want to contribute and you want to carry it on and you want to inspire, participate that way. You don't have to have a job. You could just, as a hobby, you don't even need a telescope at first. Just kind of get plugged in, find out who's having a telescope party or night viewing. I mean, yesterday was awesome. We had the virtual stargazing with the telescope down in West Virginia. And so, I was in my living room looking up at all these observations. It was awesome. The images coming down. Dr. Miller was running the show. She had all these, had the telescope moving and the dome was open, and students and faculty were just sharing their favorite views of the sky. Awesome. You don't have to be a teacher. You don't have to be an engineer. You don't have to be an astronomer. You just got to have a passion for it. I think you can contribute that way. People see that, they like it, and you know, it just propels it forward.
Okay. Well, we are just about out of time, so I think it's time to wrap up this session. Thank you so much, Carl, for your presentation, and thanks to everyone for attending. I'll just leave with a plug for the concluding remarks session that will kick off at 4:50, featuring Dr. Ed Albin, the chair of the Space Studies Department at APUS. And we hope to see you there.
All right, everybody. Thank you so much. I really appreciate it. I'm humbled to be here every time. Thank you. I enjoy this so much. And my email, the school has my email. If you want to get in touch, get in touch. I'm more than happy to help in any way that I can. Thank you so much.
Thank you, Kinjo.